Okay, today we're going to talk about centroids. These are not necessarily a statics topic, but they sort of fall into some of the things we need in order to do strength of materials. But they don't really have they don't have forces on them. What we're talking about here as a centroid, you could relate. It's not the same, but you could relate it to center of gravity. But we're talking about centroids of a planar shape, like a cross section of a beam or something like that. So it's not a volume. You could have a centroid of a volume, but we are only doing two-dimensional cross-sectional centroids. So the idea here would be if you had a shape of some sort, maybe just like a rectangle, and you wanted to balance that. This is relatively 2D. It does have some thickness to it, but it's relatively 2D. You wanted to balance it on some point, then that point would be its centroid. And in that sense, it does correlate to center of gravity, except that, like I said, we are going to do 2D, no volume, no thickness at all shapes, and so they don't really have weight or mass at all, so it's not the same as center of gravity. Let's start with just kind of a not derivation so much as just an explanation of where all these things are coming from. So I'm going to start with a circle. We'll make it a shaded in circle, and let's put it in a coordinate system. So maybe there's an x-axis, maybe here's a y-axis. So it has some x and y coordinates. Again, we're thinking 2D. Well, actually right now we can think of this as a sphere, and maybe it has a weight. So for now it can be three-dimensional object, and that's fine. So I have this one weight. And let's say it's not very big. It's kind of small sphere, and I know where its centroid is. It's right there in the center of it. So I don't really have to calculate anything. I guess I could measure it if I could measure from the y-axis and measure from the x-axis and get the x and y coordinates of this sphere, and I would know where that centroid is. Let's add another sphere, maybe over here. This one will have its own weight, and its own location, and now in its own centroid. Like each one of these spheres, sphere 1 and sphere 2, would have their own weight, their own centroid location, own center. We don't have to worry about centroid right now, but center. And they're in these positions in this coordinate system that I've created. What if I wanted to know the centroid of the group? So the two of these, or if I had 3 or 4, or a whole field full of these spheres, what if I wanted to know the centroid of the group? So what I could do is I could guess, but depending on how much these weigh, this one has weight 1, this one has weight 2. This one has a distance that would be in the x direction, so x1. This one has a distance x2, and I could measure those things. I could also measure in the y direction if I wanted to. Right now, let's just focus on one direction, but I could measure in the y direction to get the location of these spheres. But if I wanted to create an equivalent sphere, a single sphere that had the same kind of effect weight-wise as these two spheres, kind of like replace the two with one single larger sphere, where would I put it and how much would it weigh? It's relatively easy to figure out how much it would weigh. It would just weigh W1 plus W2. That would be the total weight. So that's relatively straightforward. And if I had a whole bunch of these, I could just say that, well, that just equals the summation of all of the weights. However many I have, I just add them all up. So the total weight, this T here I'm talking about is total. That's relatively straightforward to figure out. You know, the equivalent weight is just add up all the individual weights. But where do I put it to have the same effect? And so then you have to think about, well, what kind of effect do you even mean? So what we're talking about here is that each one of these spheres, sphere 1 and sphere 2 plus sphere n, you know, however many I have, they all have some distance from the x and y axis, and therefore a distance from the origin of my coordinate system. And if I have a force or weight that is some distance away from a reference point, an axis or a point or whatever it is, then a force times the distance creates a torque or a moment. We call them moments, and we reserved the word torque for when there's a shaft involved. And so maybe it has a moment. So I could go in and I could say, well, I know that probably I'm going to have to put a larger sphere somewhere in between these two. And I know that its weight, the equivalent one, would be WT, the total weight. I just need to kind of figure out where to put it. With 2, if the weight 1 and weight 2 are, you know, if they're the same weight, then I could just average them and put them in the middle. But maybe they're different weights, or maybe there's more than 2, and it's harder to figure out where the middle is, because it might be weighted heavier towards one side or another or whatever. But I can create the same effect. And the effect I want to create the same as is, I want to say that if I take WT, the total weight, and multiply times this distance, I'm measuring everything from the y-axis right now. I'm going to call this x sub c, so this will be the location of the centroid of the group. So if I take that WT, total weight, multiplied times xc, that would be a moment. So that is a force or a weight times a distance creates a moment. And I wanted to have the same effect as all the individual little spheres, W1 and W2, added together. So this effect needs to equal W1 times X1. So that's the moment, well, not Xi, X1. That's the moment that the little sphere 1 creates about the y-axis. And add on to that W2 times its distance from the y-axis. Now, you might think that these forces are going in the y direction. Don't worry about, you know, which direction is this moment being created. Just I'm trying to create the same effect. And so this side is the total weight placed at some distance x sub c, and it has the same effect as far as force times distance goes as all of the individual ones added together. And I could have, you know, millions of them or 2 of them or whatever. If I had 1, then it's basically just on top of it, right? But if I have more than 1, then I have to add all the little individual weights together, multiplied by all of their individual distances from my reference point. In this case, the reference point is the y-axis. And now I've got this kind of equality, and I know everything in this equation except for this value. I know the total weight because it's just add up all the individual weights, assuming I know all the individual weights. And again, here are all the individual weights. And then I can measure where each one of the individual weights is. And so I can solve this equation for xc equals w1 times x1 plus w2 times x2. And I'd need to divide by the total weight. And I have an equation that I could generalize it a little bit. So I could say xc equals, in my example, I only drew 2 little spheres, but there could be many of them. And so I could just take and sum all no matter how many there are, from I equals 1 to n, I could sum up all of the individual weights times their individual locations, and then I could divide by this total weight, which would just be the summation. I guess I could write that as a summation also, couldn't I? I could write that as the summation of I equals 1 to n of all of the individual weights. So I could kind of generalize this equation. And when I do that, this x sub c, that is the location, or the x coordinate anyway, of the centroid of where I need to put this equivalent weight. So I'm solving for the centroid, or at least the x component, or x coordinate, of the centroid, in this case of the group of spheres. And I could do the same thing in y, except instead of taking the weights times their distances from the y-axis, I just take the weight times the distance from the x-axis, and then I would end up solving for all those distances would be in the y direction, and so I'd solve for the y coordinate, and it would look very similar. The equation would get some room. In the end, the equation would look like y sub c equals the summation of wi times yi over, well, let's just say total weight, wt. So this gives us a general way to think about this centroid. The centroid is the not necessarily center, not necessarily middle, not necessarily center of gravity, but it's where you could put an equivalent mass that has the same moment effect about some reference point, the y-axis or the x-axis or whatever it is, as all your individual components that you might be dealing with. We still have it listed as a summation, and we still have this idea of a force or a weight. And I said we were going to talk about 2D things. So let's see how we're going to apply this idea, but just to 2 dimensions. So first of all, if we think about weight equals mass times gravity, or acceleration due to gravity, we'll do g sub c, I guess. In practice, pretty much anything you design engineering-wise is going to be in a constant field of gravity. So you're not going to really have to worry about one end of your part being in a 9.81 meters per second squared acceleration from gravity, and another end of the part being in a different acceleration due to gravity. You know, maybe if we start building space elevators or something like that, then we can worry about that. But for most things that you're going to deal with, a beam in a building or something like that, it's in a constant gravitational field, and we can say that, well, yes, this is true, but weight is going to be proportional to mass. And then I could say, all right, density is equal to mass over volume. We just know that. And from here I could say, okay, mass is has to do with the amount of material that I have. Density, let's just put rho, equals m. Density is just a material property. Again, we're going to assume that most materials that you work with in an engineering context are going to have a constant density. It's not necessarily true. There could be materials and even reasons why one piece of a thing that you're working on has one density, and then it changes that density in the cross section or along its length or something like that. It is possible, but it's not often that that's going to happen. So in general, density, or the density of the material that you're thinking about when you're wanting to solve this centroid. A lot of times we're going to solve this centroid because we need to calculate stress in a beam, or some sort of deflection or things like that, and we probably don't need to worry too much if the material is changing properties, density properties, from one piece of the beam to another piece of the beam. So density is mostly constant in an engineering material. Again, you could have special reasons why it's not, but in general, and in this class, it is going to be constant in our engineering materials, like a steel beam or whatever. Volume is, let's look at a cross section of something. Let's just have some random shape over here. So I don't know why we would have a beam or some element shaped like this. Maybe it's a bracket. And the cross section is, or the volume of this bracket is just the cross-sectional area, which would be this piece, times how thick the thing is. So that's the volume. That's how you calculate volume. You take a face and then multiply that face times how thick the thing is, and you get its volume. So this one does have a little bit more limitations. So I can't have things like a sphere, where that's not the way you calculate the area, or a cone or something like that, where it does change cross-section from one end of the part to the other end of the part. But in the scope of what we're usually going to be doing this centroid with, we're talking about maybe an I-beam, where it looks like kind of capital letter I, and it has some length to it, but along that length, it never really changes anything from that cross section. It pretty much looks like this I all the way down, or maybe it's a channel beam, or maybe it's a rectangular beam like a 2x4, or who knows. Most of the elements that we're going to worry with, they don't change their cross section from one end to the other end of the thing. It stays that same cross section. So I can also say that as far as the thickness goes, most elements, so beams, brackets, plates, stuff like that, don't change their cross section from one end to the other. So if I take those two things, that the density, it probably is, if it's at steel at one end, it's probably steel at the other end of the beam. And if it's a I-beam cross-section on one end of the beam, it's probably that same I-beam cross-section on the other end. Then I can take this equation and say that, well, the area is proportional to this mass. And now I have a reason to just be in 2D. The area is 2D cross-sectional area. And so I've gone from originally, when I talked about this idea of the equivalent centroid of a central mass that represents all these individual pieces, and it had a weight, which was a force times a distance, so it created this moment. And I went and said, well, weight is proportional to mass as long as I'm in the same gravitational field, which I should be. And mass is proportional to the cross-sectional area, assuming that the material doesn't change density somewhere along its size, and it doesn't change its cross-section. So the one that's the most constraining here is that it doesn't change its cross-sectional shape. So when we're talking about these particular calculations for centroid, we really are talking about things like I-beams and rectangular beams and things like that, where it is a 2D shape that represents an entire volume of material. And as long as that 2D shape, the cross-section, can represent that entire volume of material, you just kind of extrude it out, then we're okay. if you have something like a cone or a pyramid where the 2D cross section is constantly changing as you move through the cone or the pyramid, then these centroids won't really work for that. So I'm going to take my equations that I did write, this x sub c and y sub c here, and I'm going to rewrite them, but instead of w's, weights, I'm going to just deal with the cross-sectional area A. So x sub c is equal to the summation of area AI times xi over the total area. So not necessarily weights anymore. I just took this equation here and substituted the weight as an area, because the area represents the weight, assuming I make all these same assumptions that we just walked through. And y sub c, same way, would be the summation of AI times yi, where yi is the individual distance from the x-axis, in this case, the reference axis, in the y direction to whatever this area is that I'm talking about. And so in my first example, the area were all these little circles. We do need to divide by the total area. This numerator has a specific name. In either case, it's the same name, whether it's the x or y. These things are called the first, and they do use the word moment of area. And it's moment because where it's coming from, this numerator originally was a force or a weight times a distance, which really would be a moment. But then we've assumed that it's this constant gravitational field. We assumed a uniform cross-section throughout the thickness. We assumed a uniform density. And making all those assumptions meant that we could, instead of having to deal with an entire volume of material, we could just deal with its cross-section. And so it's the first moment of area, even though an area doesn't really have mass or anything like that to create a moment. But that's what it's called, first moment of area. You might notice that it's probably not too useful all the time to just have all these little circles. So what we could do is we could also write these equations, x sub c, instead of doing discrete little pieces, little circles, we could just integrate. And we could, instead of having summations, we could have integrals. Let's actually not do a in there. Let's do x dA. And then integrate just dA to get the total area. Y sub c is the integral of y dA over the integral of dA, and we could integrate over the area, the differential area dA. Why don't we set up a problem to do exactly that? I'm going to go to MathCAD. We'll just have to remember these equations that we're dealing with, and let's just copy them, and then we will drop them over in MathCAD. Oh, hold on, I didn't copy it right. There we go. Now let's go, there's MathCAD. Let's drop those equations in just so we still have them. Wow, that's gigantic. Make them a little smaller. So there they are. And let's create an equation, y of x. And we will use, I had one already picked out, y of x equals 3, oops, not in the right window, 3 times x squared plus 5. So let's plot that so we get an idea what it looks like. So we're going to plot, I'm not using units on these, we're just going to plot them without units and it'll be fine. So y, oh, we need to plot against x, not s, x. There we go. So it's just a parabola, but let's only take a certain piece of it. Let's go from 0 here over to 3 here. And let's say that this is what our shape looks like. In fact, let's copy it so I can actually draw on it a little bit. So we'll go back over here and paste this guy in. So just to be clear on what this area is, it's kind of like the one I drew right here, where it's got this parabolic shape on the top, rectangular everywhere else, and it's extruded into the paper or into the screen. So our shape would look, you know, well, I guess that's blue, something like this. And then it has depth into the page or the screen. So something like that. That last line might make it more confusing. So it goes into the page. So how are we going to integrate this? What we're going to do is we're going to pick a stripe, either a vertical or horizontal stripe. So I'll draw those in there. We'll either pick this kind of stripe, where this distance is dx, and we integrate from x equals 0 to 3, and so we would end up adding all these little strips together, just very similar to how we added all these circles together, except now they're differential strips, so they're infinitely thin. We could do horizontal also and have a dy thickness, but it's actually going to be a little easier in this case anyway to do a dx thickness, and the height of these, remember our equation, y of x equals 3x squared plus 5. That's the equation of this line. So I know the height anywhere because I know that equation. So this piece, any one of these, it doesn't matter which one you pick, but this one, let's say, that is dA. So each one of these guys is dA. And dA would equal the height of any one of these rectangles, whichever one you look at. The height of it is defined as y of x, because that's the equation that defines the top line of our shape here, y of x, times the width of the rectangle, which I have labeled as dx. So taking that, I can look at my equation. Let's just do x sub c. So x sub c equals the integral of x times dA over the integral of dA. But I just said that dA is this y of x times dx. So x times dA is y of x dx over the integral of dA, where dA is y of x dx. In this case, I need to integrate from 0 to 3 because I've put my limits at 0 for one edge of the little bracket and 3 inches or whatever it is at the other edge of the bracket. So let's go back to MathCAD and see if we can code this in and calculate. What it'll give us is the location for the x-coordinate of the centroid of this parabolic-ish shape. All right, so let's see. Oh, well, let's do x sub c equals this. So x c equals the integral from 0 to 3 dx, and then we're going to put in what we're integrating is x times y of x, and y of x I've already put into MathCAD. So y of x is this equation 3x squared plus 5. So x times y of x. Okay. and then we divide all of that. That's the first moment of area. We divide it by the total area, which would just be the integral of from 0 to 3 again, dx, and then just integrate y of x, so the area under the curve. And if it equals, let's assume these units are inches. I don't really know. I didn't build units into it. So it says x sub c is 1.982. So if we went to somewhere right in here, that would be where we would find the location for the x coordinate of the centroid of this shape. So going back to this one, it puts the centroid somewhere on, it said almost 2, so somewhere on this line. That's where the centroid would be. To find the complete location, we need the y coordinate also. So y coordinate, we need to solve this equation. Y sub c equals y dA over integral of dA. Now this one, we do have to think a little bit more about what was going on here. So remember, this numerator is the first moment of area. So we're trying to recreate the effect of like a moment. And so, but we're not dealing with weights and forces. We've simplified it down to just an area. And when we're doing it with a calculus approach, the area is just this little differential strip that I colored red. And we do a whole bunch of those from x equals 0 to 3 in this case. So this numerator is also the first moment of area. And when I want to think about that, and I'm using these strips, if I think about the red strip being an actual bar that has weight and mass and all that, and a force associated with those things, and I wanted to calculate the moment that that bar creates about the x-axis, I wouldn't multiply times this distance, you know, the whole height of it. I would multiply for the distance. I would multiply the force. In this case, the force is represented by the area. I would multiply that times this distance. That's how far it is away from the x-axis. It's easier to see in the when I'm doing the x direction, and these little differential strips are really thin, and this is the distance I'm using from the y-axis. That just is x. But when I'm talking about the measuring the distance in the y direction, I don't want to measure all the way to the top of the little differential strip. I only want to measure halfway. So this distance is 1/2 y of x. So it's only half the height of the differential strip. So I do have to keep that in mind. So let's go back over to MathCAD. Again, I did paste our equations in here. Y of c, I guess we can put it over here since I put this other one over here. Y of c equals the integral. Again, we are still using these vertical strips, so we're still going to integrate from x equals 0 to x equals 3. We're still going to integrate dx. Whoops, I already had the d there. X. And then our numerator is y, not y of x, but y meaning the moment arm. So remember, this came from these moment arms. I just never drew the y ones. On here, the y would be, you know, this distance to the center of the shape. This would be y sub c here. This would be y2. I didn't draw them because it gets really cluttery. So the center of the shape, we're using these differential strips where the center of the shape is half of its height. So y of x is the height of the shape, the differential strip, divided by 2, times dA, which we don't have dA written on here. dA was y of x, the actual height of the strip, times dx. I already have the dx in there, but I need to multiply this times y of x. This y of x I just wrote is y of x times dx is dA. All of this needs to be divided by the total area, which is just the integral. It doesn't matter if I do x or y here, so I can just do 0 to 3 y of x dx. So this equation, when I evaluate it, should give me where to put the y coordinate, 9.314. So that looks like there's 10, so it's right underneath there. So that distance is y of c, and this point right here where they both cross, that would be the centroid of this bracket or this plate that's got this parabolic curve on top of it, or whatever you want to call it. That would be its centroid. If it were an actual object, it had thickness and it followed all these rules where its density doesn't change, the cross section doesn't change through the thickness, it's in a constant gravitational field, all those rules, then if you cut this thing out, this is where it would balance. So it would be the center of gravity, assuming all this other stuff is true. All right. Do you always go in and integrate every little shape? Say you actually were working with one of these I-beams. Do you go in and try to create an equation that describes the I-beam cross-section? I suppose you could, but there is a simpler way. So I went through this process with the calculus because it reveals how the centroid is working and some of the assumptions that are embedded in using these equations to calculate centroids. And I think it gives you an idea of what to do if you did have a shape that wasn't just some standard rectangle or circle or something like that. But most of the time, you're dealing with shapes like I-beams that are just made up of primitive shapes. They're made up of rectangles and triangles and circles and semicircles, and there's 5 or 6 primitive shapes that you could cobble together to make most any cross section that you're actually going to use in a design. Now, I guess that is changing because more and more engineering designs are becoming optimized. You have topology optimization and things like that in computer-aided design where you can take a regular shape like an I-beam and then run simulations on it to create the optimized geometry where these assumptions are no longer true. Particularly the one about it staying a constant cross-section throughout its whole length. That can be less true than it used to be. It's still not very mainstream, and it's still only in pretty niche applications where you really do have to have the minimum amount of weight spent on building this structure, and you usually have to do some either very sophisticated machining or some additive manufacturing process to create the geometry anyway. So it is slowly changing to where maybe these assumptions aren't always going to be as true as they once were, but for the time being and for the foreseeable future, these assumptions are still going to be true. You're still going to build things out of rectangles and I-beams and tubes and pipes and stuff like that. So what we're going to do is we're going to take a chart. Let's see if I can find a good chart. I think I have one on Moodle. Let me see if I can dig it out. I didn't think about needing to find it until just now. All right, in here. So this is in the Introduction tab. There's a reference materials folder. This is where we found the material properties previously. And here is a chart for centroids. So we're going to look at that. Well, it isn't just a blank page. Maybe if we, there we go. Just have to make it wake up. So here we've got a book scan, and you can find these. You can just search for centroid chart online, and you can probably find a better one to look at than this one. But there are, well, first of all, there's these 6. These 6 are for volumes. We are not going to need to use any of the volumes, centroids of volumes. You can calculate centroids of volumes, but we're not going to need to do that. And you can even find a parabolic spandrel here, which we could probably use this equation or this set of equations on the example we just had that we did by calculus. Most of the time, you're going to be using this rectangle, this semicircle, maybe a quarter circle, and a triangle. And then there's some specialized triangles, parabolas, arc. These 3 over here that aren't colored in, these are like you took a piece of wire and bent them into these shapes, this circle, or semicircle, quarter circle, and sector, or circular arc. You're not often going to use these because most of the time when we're dealing with centroids, we're talking about centroids of a cross section of a beam or something like that, not just of an arc of wire. So what these tell you is basically these are for these particular shapes. Someone has gone in, done this process for a rectangle or for a quarter circle or for a semicircle, and given you, instead of a number here, they evaluate this integral for you with variables, with base and height, usually b and h, sometimes r for radius. And you can see in the chart where, let's zoom in on one of these that's obvious. They did put a rectangle in here, although it should be intuitively obvious where the centroid of a rectangle would be. It would just be in the base divided by 2, so you can kind of see x sub c, and they've got it labeled down here. X sub c is just the base divided by 2, and that's where the centroid would be. Same thing for the height. It would be the height divided by 2 to get the location of the y centroid. Some of these are not as obvious, like this semicircular arc area, not arc, area. You know it's somewhere near the top, not necessarily right in the middle, but you wouldn't by default just know that it's 4r over 3 pi. That's a thing you'd have to either go and calculate it this way, or look it up in a chart this way, and eventually you'll remember these just by using them enough. So what do we do with this? Let's continue on over here, and let's create a pretty generic shape. Not MathCAD, let's actually go here. And let's create a T-beam. That's a relatively common beam shape in construction. So this is it's got a really wide stem, and flange is kind of average shape. So this part up here is the flange, and for a T-beam, this part down here is called the stem. On an I-beam, it's called the web. Let's put some dimensions on this, and I'll just use the ones that we kind of drew. So this will be 2 inches. This will be 1 inch. This will be 1, 2, 3, 4, 6 inches. And then this one, 1, 2, 3, 4, 5, 6, 7, 8 inches. I think that's all we need. And we'll assume it has bilateral symmetry. So there's a axis that, if we drew an axis right here, this part is symmetric about that axis. We'll put the x-axis down there. So what we want to know is we can look at it, and assuming it has this symmetry, then we know that based on where I drew the origin, x sub c is 0. We know that somewhere the centroid, it lies on this y-axis. Now, if I put the y-axis somewhere else, that's not true, but it's on this line, whether or not this is the y-axis. So how I can do this is my chart that I have has equations for the rectangular shapes, and we know them intuitively. X sub c is half of the base, y sub c is half of the height. We know that. But instead of using the integral form, now I'm going to go back to the discrete form with the summations. And if I were well, x sub c I did by observation, so I don't need x sub c. Let's do y sub c. So x sub c equals 0 by observation. Y sub c equals, instead of doing calculus, let's do summation of ai times yi over the total area. That is the equation that we had right here. Okay. What I can do here, now you could just write this equation out. It's pretty straightforward. There's only a really simple T shape. I'm going to draw out a kind of a bookkeeping process, because they do get more complicated the more pieces you begin to add. This is about as simple as you can get. So the first thing you need to do is figure out how are you going to break this T shape into shapes that you do have knowledge about. And so the shapes you have knowledge about are these, the rectangles and the arcs and these triangles over here. So T, the way I drew it, can just be broken into one rectangle that's the flange, chop it kind of right here, and a second rectangle that's the stem. And that's those two pieces, that's enough to create this T shape. So I can, my bookkeeping method would look like this. I have the parts, part 1 and part 2. I usually draw a little picture so that I kind of can figure out what I'm talking about versus trying to describe them or just number them. I usually draw a little picture. Each part I need to know the area. These are all in inches, so it'll be inches squared. The area of part 1 is 8 times 1, so it's 8 inches squared. The area of the stem, 6 times 2, that's 12. Right there, I can get the total area is 20 square inches just by adding that column. The other thing I need, I have the area, I have the total area, I need the individual distances for each part. So this yi, that corresponds way back up here to when I was dealing with these circles. Each circle had its own distance from the reference. In this case, I'm referencing the x-axis, and each circle has its own y sub 1 or 2 or whatever, c. So in my bookkeeping method, I go in yi, these are going to be measured in inches, and I find where's the location of the centroid for just rectangle number 1. So a lot of times I'll go in and actually draw the centroid of rectangle number 1 and the centroid of rectangle number 2, and then I can get a better idea of, okay, I'm measuring from the x-axis down at the bottom 6.5 inches up is where I would measure this distance. So this distance here, that's y1, 6.5 inches. This one, y2, is 3 inches. So it's half of the height of the stem. Okay, so I'd put 3 inches. Then the equation I'm solving has me multiply a times y and then add up all of those multiplications, all those products. So a times y, the units on that will be inches cubed. It's not a volume, but the inches squared times inches gives me inches cubed. And I would have, and part 1 has an area of 8 and a y distance from the x-axis of 6.5. Multiply those and you get 52. 12 times 3, you get 36. It is possible for these to be negative. Like maybe from your reference axis you have to measure in the negative direction. So you could have a negative distance. That's totally reasonable. You could even have a negative area if instead of a T shape like this, maybe I had a rectangle that had a hole drilled in it. And so I've got a rectangle with a negative hole or negative circle that creates the hole. In this one, they're all positive. The numerator says I need to sum all the a times y. So 36 plus 52 is 88. That would be the summation of ai times yi equals 88 inches cubed. And then y sub c equals summation of ay over total area. And I have those two numbers, 88 inches cubed over 20 inches squared. My units come out in inches, which makes sense. 88 divided by 20 is 4.4 inches. So what that says is that the location of the centroid is 4.4 inches above the reference. I was measuring everything from the x-axis at the bottom of the T. You can put your reference wherever you want to. I just put this one at the very bottom. So if I measure up 4.4 like that, this intersection point is where the centroid of the entire combination of these two rectangles would be. So we're doing the exact same thing that we did with these spheres, except we've turned them into flat pieces. So instead of like plates, they are just rectangles. And we have made them touch each other so that they're, joined together. They can or can't be, it doesn't matter. But as far as finding the centroid goes, as far as it being a beam, they should be joined together. And again, we could have short-circuited all of this bookkeeping method. We don't have to go through all of this process. But for more complex shapes than a T, it's useful for keeping track of things. So I did have a more complex one pulled up here somewhere. Let's see if I can find what I did with it. Here it is. So here's a composite centroid, and we've got, there's arcs in here, there's holes, triangles, rectangles. Let's see if we can do this one and find X or Y or maybe both. Depends on how long we want to spend working on this. But let's work this problem as a more complex example of the discrete version of finding a centroid. Let's see. That looks like it. There we go. We've got all our dimensions for everything up here at the top. I might write those in because it gets annoying having to, reference back and forth. So B is, for mine, 6.7. These are all inches. I'm going to leave the units off just to kind of keep it less cluttery. A, 7.6. Another A. C, 7.3. And D, the diameter of this hole, 5.2. All right. So we've got to figure out how are we going to assemble this part. And there's multiple ways you can do it, and there's not necessarily one way that's right. There are multiple ways you can get the right answer. Some of the ways might be a little more simple than others. What I think I'm going to do is I'm going to create 1, 2, 3, 4. I'm going to create 5 parts. So one part is this piece, which is just a square, no, it's a rectangle, b times a. Part 2 over here, that's going to be a quarter circle, solid quarter circle. Part 3 is going to be a triangle. And part 4 is another rectangle. And then part 5 is this hole that I'm going to cut out of everything. So it's actually going to have a negative area. Since this is a problem that's given to me, I don't really get to choose where the reference axes are, because if I move the reference axes, then that'll change the value of x sub c and y sub c. So my origin does need to stay here in the middle. So if I'm using my bookkeeping method, I'm going to have 5 parts. 1, 2, 3, 4, 5. Part 1 is a little square. Part 2 is a little quarter circle. 3 is a triangle. 4 is another square. And 5 is the hole in the middle. Each one of these parts has an area. And these were in inches, so I can put inches squared here. Area of part 1 is, I can't see the numbers, 6.7 times 7.6, 50.92. Quarter circle area, I have a radius here, basically, 7.6 inch radius. So pi times 7.6 squared, pi r squared. But I'll only have a quarter circle, so divide by 4. 45.36. This triangle, part 3, has a base of 6.7 and a height of 7.3, but it's a triangle, so divide by 2. 24.46. Square number 4 is 7.6 times 7.3. 55.48. And then the circle in the middle has a diameter of 5.2, so pi times diameter squared divided by 4, but it's negative because it's cut away. So all of these others were positive and created a solid shape, and now I'm using the negative area of this circle to cut a hole in the middle of it all. So negative 21.24. And if I take the summation of this column, that's the total area of my little bracket. So 50.92 plus 45.36 plus 24.46 plus 55.48 minus 21.24, 154.98 inches squared. It's really tempting to do these in Excel because this is, I'm basically doing a spreadsheet here. The only problem is it's harder to track down errors, at least to me. But if you want to do them in Excel, you can for homework. But on the exam, you're going to have to do them just on paper. So just be aware of that. And there will be, on an exam, this is on exam 1, by the way. I don't know that there would be a part with 5 pieces you have to deal with. Probably more like 3 pieces. 5 is, it's pretty tedious to work your way through all of that and get it right. All right. So let's do the x coordinate of each of these pieces. So the x coordinate of part 1. So it's important to note that the y-axis is right here. And the x-axis for this diagram is right here. So the y-coordinate of part 1, it's and it might be good to go in and draw the centroids of each part where you think they are roughly. The centroid of part 1 is to the left of my y-axis, so it actually gets a negative number, and it would be negative 6.7 divided by 2. Part 2 is a quarter circle. You probably don't know where the centroid of a quarter circle is, so that's where you need to go and find your, let's see if I can find our sheet. What did we do with our sheet? Oh, it's on this page, but no, there. There's a quarter circle right there. They have x sub c. Sometimes you have to mentally reorient where these reference axes are, because maybe the quarter circle is turned differently from what you have in your reference material compared to what you have on your problem you're working on. So this one is not, though. This one is exactly the same. X sub c is 4r over 3 pi. Oh, wrong page. 4r over 3 pi. So the radius is 7.6. So 4 times 7.6, 4r, divided by 3 pi gives me 3.23. And that one is positive, because it's on the right side of the y-axis. The triangle, again, maybe another one that you don't immediately know where it's at. So you go check your reference material. This one is oriented differently than what our picture is. So here you have to figure out what is this x sub c telling you. So it says that x sub c, if I measure from the thinner end of the triangle and I measure over 2/3 of the base, I will reach the centroid. Or if I measure from the larger, it's not labeled, but if I measure from the larger side of the triangle to the centroid, that's 1/3 of the base. So looking at our picture, I need to measure from the larger side of the triangle over to the centroid, and that's going to be 1/3 of the base, and where the base is this 6.7, and it's negative. So 6.7 divided by 3 is 2.23. Negative, oops, I don't want it green. Negative 2.23 inches. Then we're back to a simple one with square number 4. 7.6 divided by 2 is 3.8. And then the hole in the middle is actually at the origin. They don't even bother to give you a circle in your centroids. They give you quarter circles and, you know, half circles and all that. They don't give you a circle, and you just need to know that the centroid of a circle is directly in its center. And so this one, actually, the center of this circle is right on top of the origin, so it's 0. So now I should have enough information to do a times x, where I multiply all of these individual areas by the corresponding x coordinate of that area, the centroid of the x coordinate of that area. So 50.92 times negative 3.35 is negative 170.582. 45.36 times 3.23, positive 146.513. 24.46 times negative 2.23, negative 54.546. 55.48 times 3.8, positive 210.824. 0 times this one is 0. And it is positive that you, or it is possible that you have a negative area and a negative x or y, and it would make a positive number when you multiply them together. So even though it seems kind of weird that they're both negative, it does work like real math. Here we need to add these up. So 210.824 minus 54.546 plus 146.513 minus 170.582. If I did all that right, we get positive, so this will be the summation of AX, positive 132.21 inches cubed. It's also positive for this summation to come out as a, it's also possible that this summation comes out as a negative number, which just means that the centroid is to the left of wherever you put your reference y-axis. So we should be able to do x sub c equals 132.21 inches cubed over 154.98 inches squared equals 0.853 inches. Then we should check here, does that look reasonable? So it's saying that more or less somewhere on this line, if this line is 0.853 inches, that would be somewhere on that line is where the centroid is going to be for this shape. And that seems reasonable because it's more or less symmetric shape. You know, it's got the triangle versus the quarter circle. The quarter circle and the right-hand side seem to be a little bit wider than the left-hand side if you look at the dimensions. So it does make sense that the centroid is probably shifted a little bit to the right of the origin of where this coordinate system is. In this case, we can actually plug it in, 0.853, into WebWork and see if it agrees. Oh, let's try again. No. Oh, well, all right. So it's a WebWork thing. WebWork wants 0.851 and I got 0.853, so I'm off by 0.002 of an inch or less. So on an exam, you don't have to worry so much about that, but do pay attention that every one of these numbers in this chart is rounded off from what the calculator says. So that is where WebWork actually makes these problems a lot harder than they need to be because of its such tight tolerances. That is a reason why it might be good to actually do these in Excel to try and, you know, eliminate rounding because we're off by 0.002 of an inch and it says it's wrong, which is kind of crazy, but that's what it says. On an exam, this would be a perfectly fine answer. And not just because I did it, it would just be fine. Let's do y sub c. Maybe we can get that one right. Y sub c. So here, I'm going to measure everything from the x-axis, so horizontal. So part 1, half of 7.6 should be 3.8. Positive. The quarter circle might have to go check our little chart. Turns out that y sub c and x sub c for a quarter circle are the same calculation, which makes sense when you think about it. So 4r over 3 pi. So it's actually going to be the exact same number, 3.23. It's the same radius, and 4 pi and 3 are constants. The triangle, it works the same way. We specifically looked at the x-axis last time, but if you look at the y, it does the same thing where if you measure from the larger side of the triangle up to the centroid, y sub c is the 1/3 of the height. And if you measure from the pointy end of the triangle down to the centroid or over, it doesn't matter if it's up or down, that's 2/3 of the height. So from us, we're measuring from the wide side of the triangle to the centroid, which is the 1/3 of the height. So 1/3 of the height, 7.3 divided by 3. 7.3 divided by 3. 2.43, but we had to measure down from the x-axis, so this is a negative. 2.43, and again, there's a bunch of 3's out here that I'm rounding off. The square 4, 7.3 divided by 2, gives me a negative 3.65. Hole in the middle, is still in the middle, so it has 0 distance from the y or from the x-axis. And now I can do a times y. And I have, well, let's see, 50.92 times 3.8, 193.496. 45.36 times 3.23, 146.513. 24.46 for the triangle times negative 2.43. So negative 59.438. 55.48 for the square number 4 times negative 3.65 is negative 202.502, and then 0 times anything is 0. So here we have the summation of AY is 193.496 plus 146.513 minus 59.438 minus 202.502. 78.069 inches cubed, and y sub c equals that 78.069 inches cubed divided by the same area total that we had before, 154.98 inches squared, 0.504 inches. And we'll check WebWork just to see what it thinks, but it'll probably tell us we're wrong. 0.502, so we were at 0.504. That's probably not going to be close enough for it, but we'll give it a shot. Nope, it really wants the 0.502. So again, off by 0.02 of an inch. Not a big deal in the real world, but in WebWork world, it cares about that. So again, this one is probably a little bit more than any you would have on an exam, but it's not unrepresentative. It is similar to the type you would just have maybe 1 or 2 fewer pieces to deal with, and you wouldn't have to get down to the 10,000ths of a decimal point to get it right. So this says what, 0.5? So somewhere, I don't know. Right in here is 0.5. So this intersection would be the centroid of our composite shape. So that, again, we have plenty of time left. So if you have any questions, go ahead and put them out in the chat or something so I can see them. But I think this probably gets you far enough moving towards how to calculate these centroids, both calculus and composite. And you have a new homework set. It's homework 11. So we skipped a couple of homework sets because the order they were originally in doesn't do centroids at this time. It does, I think, frames and machines. So the number might seem weird that we're skipping some, but it's because I'd rather do centroids now versus frames and machines. We'll start frames and machines after exam 1. All right. I think we're good. Work on those homework problems. I haven't had too many questions about anything yet. Most of the questions have been WebWork rounding errors versus an actual misunderstanding of something. But if you have some issues, just send me an email or a Discord or a chat or whatever, and I will try and sort it out for you. I do have Zoom office hours also if you prefer that you can get an answer that way possibly. So I think we'll stop here. I don't think there's going to be anything gained by doing yet another centroid problem today. But tomorrow we will kind of review everything. So I haven't labeled, not tomorrow, Monday. Monday I haven't labeled as centroids, but think of it more as kind of a review of all the stuff. So we'll do some centroids, some trusses, some stresses, kind of all combined together. And that Thursday of next week is exam 1. All right, I will see you guys Monday.